In this video, we'll be looking at section 4 of the radioactivity and nuclear energy topic, radioactive decay. As you know, radioactive decay is when an unstable nucleus randomly decays by giving out alpha, beta, or gamma radiation. Now, this is an impossible thing to predict, hence random, whenever we're talking about a single individual decay, one single nucleus breaking down. Now, the whole purpose of breaking down is to reach a form of stability, but this can take quite a lot of different decays. Different half-lives mean this will take a different time. So we have a decay constant to describe the probability of a nucleus decaying. Now we use the unit Becquerel, BQ, to describe the number of decays per second, which is the activity of a radioactive source. In terms of mathematics, there's quite a few different small equations that link together to allow us to understand activity. The first of which, listed on your equation sheet, is delta n over delta t, giving you minus lambda n. Now, n represents the number of nuclei, usually the number of nuclei present or remaining, or however you want to phrase that. Now, delta n obviously represents change in the number of nuclei, whereas n on its own is number of nuclei. T representing, as usual, time, delta t, change in time. Now I'm going to put this as seconds, but there are tricks in how you can manipulate this, as we'll see in the example later on. Lambda, as we say above, is decay constant. That is a value that you will either be given or have to work out using one of these equations. Now, as this is the decay, it's negative, so it's changing in the negative. It's always going down. But we can similarly refer to it as activity, the emission of alpha, beta, and gamma during decays, which is just the product of lambda and n. Now, this is the easy part, really. It's usually used to determine the decay constant. And A activity, as we've said above, is measured in the unit Becquerel, BQ. Now, the real, more challenging equation to use is the next one that we'll look at here. So what we have is n equals n naught, which represents the number of particles originally in an atom, multiplied by e to the minus lambda t. Now, yet again, lambda is the decay constant, t is time taken, n is our number of nuclei currently present in the source, and n naught is the original number of particles present in that source. Now, we only care about the isotopes that are actually decaying. So it's a specific type of atom that we're looking at. They will label that, and it's the number of those atoms, for example, carbon 14 that has decayed. How much was there? How much is there now? Now, this equation does require a little bit of extra mathematical skill, which we'll look at shortly, but the main trick is the fact that we're shown that this relationship A equals lambda n. As a result, if you were to rearrange it such that n equals A over lambda, we could substitute that in for n and n naught, using A and A naught, respectively. Now, lambda is just a constant, so it would cancel out, allowing us to form this equation, A equals A naught e to the minus lambda t. Now that means we have our activity at present and our original activity. which are very easy to use in terms of measured values. But this form of the equation is not given in the exam. So it is an important one to be able to derive using these two equations. Now, to look at these in terms of the mathematics behind them, we have a few tricks we have to learn here. Some of you may have covered this in maths, others not. So this structure of the equation introduces us to e to the power of minus lambda t. Now minus lambda t is usually what we're trying to work out, either the lambda or t value. Now e itself does not represent a number, it represents the exponential nature of the relationship being shown. So e itself is not just a number to take away or divide by or anything like that, but it does have an inverse function. So if we find the e on our calculator, you'll see it's e to the power of a box. That is usually the shift function above the ln button, which is the natural log. Now you may have used log previously, which is log to the base 10. ln is log to the base e. So they will cancel each other out, and that is the whole purpose. So a common question you might find here is find a value for t. Now obviously you'd be given real numbers here to actually plug in, but the algebra is just as important, so we need to be able to rearrange this equation fluidly to find t on its own. Now starting off, n is obviously multiplied by e to the minus lambda t, so we can move that to the other side. N over n naught equals e to the minus lambda t, the easy first step to take. Once we've done that, we can use the fact that e and ln cancel out by multiplying both sides by ln. Now this will bring the power of minus lambda t down, whilst also bracketing n over n naught and multiplying it by ln. So we have ln n over n naught equals minus lambda t. Once we've done this, t is easy to isolate by removing minus lambda and moving it to the other side, so you're dividing by lambda. So we end up with t equals ln n over n naught all over lambda, and we've had to move the negative over as well, so that whole side is also now negative. And that will give us the time taken for this change in the number of nuclei to occur. Now this can obviously be used as well for the activity equation, exactly the same method, and as I said before, either lambda or t is going to be your target to find. Usually t, but this rule of e and ln cancelling out is the most important part to take away from this. Moving on now, we can start looking at the half-life itself. Now you've previously covered this GCSE, and this trend is the exponential decay that we were just referring to. So this curve that gets less and less steep over time, gradually approaching but never quite hitting the x-axis. Now this is showing that even though we cannot determine the random nature of an individual particle, the more you have, the more you can estimate how long half of them can last for. Now time varies colossally with this. Days is what's listed here. Sometimes you'll get seconds, sometimes milliseconds, sometimes millions of years. Similarly, the y-axis being counts per minute can vary drastically as well. It could simply be listed as activity. Nonetheless, this graph will always work the same way. Now ideally, the y-intercept will be a nice and easy number to halve. So our y-intercept here is 80 counts per minute. Halving that, quite simply, we cut down to 40, and we can draw a line directly across to the point where it crosses the line. Drawing a line vertically down from here means we've now got a separation of 2 days represented. So it's taken 2 days for that count rate per minute to decrease by half. Now that alone is never enough. You have to prove that this is a continuous trend. So we'll need to repeat this. Going from 40, we can now easily drop down to 20. This ends up at 4 days. Now it's obviously important to remember that we're now measuring from this 40 to the 20 in terms of count, so that is from 2 days to 4 days. That means our actual gap, yet again, is 2 days, allowing us an easy determination of the half-life. Clearly it's 2 days. Now you only ever need to find this twice and find the average of these values. But don't just assume they should be the same. Very often you are actually expected to show the calculation of an average. This is a very simple example here. Now the equation representing half-life is quite straightforward, but very important when linking to our previous calculations on activity. T-half, which represents, unsurprisingly, half-life, is ln2 over lambda. Now, as we said, T-half is the half-life. And again, time-wise, depends on how you're operating. Usually you'd assume seconds, but it does depend on what you're using throughout the calculation steps. As long as you keep time with the same units, it should work out. So don't think you have to convert every time. Lambda is our decay constant, and usually that's the reason you have to use this equation is to find the decay constant, which you can then use in the N or A equations we previously looked at. ln2 is just a number. It is not anything more than a simple way of showing an awkward number. It saves rounding and making errors as a result of that, so it is literally just a number. Some sources recommend learning the number. ln2 I feel is much simpler, and this is given in the equation sheet anyway. Now, radioactive series, this section involves looking at essentially the periodic table represented graphically, as well as possible decay chains. Now, we are representing elements, or isotopes, I should say, of each element in a graphical manner using numbers that we're familiar with, like the proton number, Z, or atomic number as we often refer to it, and neutron number, N. This is not the number of nuclei, this is not the mass number, this is the number of neutrons. So that should be very similar to the number of protons lower down in the periodic table, as we have smaller nuclei. But as nuclei get bigger, and the number of protons increase by 1 each time, the number of neutrons starts to increase at a bigger rate. So using this graph, we're basically looking at the stability of different isotopes. So it's always comparative, and it shows which one's the most stable and how far they vary with their different isotopes, which is quite useful to use. Now, one thing that's often misunderstood with the radioactive sources is that when a decay has occurred, many people would assume that those atoms are now safe and stable, but they're not. It's very rare that a single decay will bring perfect stability to an atom. it very often has to undergo a series of decays. So repeated decays into different or similar elements and continuously moving towards a state of stability. And by stability, what we mean is that it can last in that form for an incredibly long amount of time before it needs to decay again. So when we look at this graph, we can see that the central line throughout this pattern, most of the way up, 2/3 of the way up, is a very, very dark zigzagging line. That represents the most stable version of each element, so the most stable isotope. Shifting from that line outwards, above and below, you end up with gradually decreasing lifetimes. Rapidly shifting to the green color for 1 year, down all the way to 1 second in dark blue, and significantly less as you approach white. Anything that is represented in white on this graph can be formed, but will immediately decay upon formation. Now, some of the higher end bits of work on this, in chemistry in particular, is trying to form elements in this top section, the heavier elements, trying to make new and stable particles. Now you'll notice the most stable particles cut off before this, so it is still a massive area of research. Now, on the left here, we can see a decay chain, which is quite fascinating to follow. As these elements, as these isotopes decay, they do sometimes revert. So you can see here that thorium turns to radium, then actinium, then back to thorium. Now it's a different isotope of thorium, but it is en route to stability. And gradually you make all the way down to the very bottom section where you can see it finally stabilizes as lead. So it is a very long process. Some of these decays will take incredibly long amount of time, others very little time. So it's sometimes very hard to determine what originally might have been present in a substance if it has gone through a chain like this. Now, we know that all living organisms are abundant in carbon atoms. It's one of our main elements. So it's not entirely surprising that we have a mixture of isotopes. Now, as we take in these elements through things like food, we will end up mostly with carbon-12, the most stable version of carbon. However, we also end up with a small percentage of carbon-14, which is an unstable isotope, so it's radioactive. Now, they will decay over time, whereas carbon-12 will not. It's very long-lasting. But throughout our living lives, we're continuously replacing these atoms. So it maintains this roughly fixed value. But once a living organism dies, it's no longer replacing these. So the amount that's present will remain the same for carbon-12, but carbon-14 will decay. And gradually you'll end up with less and less carbon-14 atoms, allowing you to compare it with a similar mass of living matter and seeing how much it has decreased by. So this brings us to the use of the previous equations, determining the age of organic matter that we have found. So as the example here says, wood. You can gauge within a range of its half-life how old it might be. So this example here, we have a wooden artifact. Okay, so it's our organic matter from an ancient tomb, contains 60% of the carbon-14 atoms that is present in living trees. So that's our comparison. Instead of 100%, you have 60%. Sometimes these are given as real numbers. Percentage is a bit simpler here. Now, the half-life for carbon-14 is given as 5,730 years. Now, the fact that's in years can lead to some calculations, but we don't necessarily need to either. And we're asked about how long ago, so we're looking for time. So we want to know the age. Now, it does ask for this as well in years, or to the nearest year. So don't leave any decimals in your final answer. But as this is being asked for in years, we already have the half-life in years. So we should not need any form of conversion into seconds. Everything we have should be fine to carry through. Now, the first thing we need to do is to determine our decay constant. As we know time is our target, we will be using one of the other equations, the more complex exponential ones, but we need the decay constant. So plugging it into this equation here, rearranged, we can find that the decay constant is ln2 over the half-life. Now our half-life, as we said, is 5,730 years, but we can keep that in years at this point. So once we plug that through, we will end up with a value of 1.21 times 10 to the power of -4. Don't worry about units, you won't be assessed on it, but keep that number in your calculator. Now, our main equation is n equals n naught e to the minus lambda t, with t being our target. Now, this equation's a bit tricky here because we don't actually have a value for n, but we do have a percentage to represent the change. So if we consider the original number as 100%, we can use 60% as our remaining amount. Now rearranging as we did earlier, n over n naught is e to the minus lambda t, and we can apply the natural log to both sides of the equation, leaving us with ln of n over n naught equals to minus lambda t. A quick rearrange, t equals minus ln n over n naught all over lambda. With this, we can now plug in our values, and as was stated, if we're taking n naught as 1, so 100% of something, and n as 60% of it, we can then say that n is 0.6 and n naught is 1. Now you could use any arbitrary numbers here, you could even use 60 and 100, but relating it to 1 when we're talking about percentages is the easiest thing to do. And that's all divided by our previous answer of 1.21 times 10 to the minus 4 that you saved on your calculator earlier. Now take care when plugging this into your calculator. I would recommend using even more brackets than I have in this instance, but as long as it is clear, it should work out. And we end up with an answer of 4,222.81 years, which you should then obviously round in your final answer in the answer box to the nearest year. Thank you for your time.